Okay, Assalamualaikum warahmatullahi wabarakatuh. Very good day. So for our class, to look on the last chapter, which is on the surface integral. So basically, this is outline of the chapter of the of the surface integral. So we will start with the surface integral of scalar field, surface integral of vector field, Stokes theorem, and also Cauchy theorem. But in this video, we are going to cover two topics only: surface integral of scalar field, surface integral of vector field. So basically, we have similar question in the line integral. So in the line integral, we have line integral of scalar field, and so we have in the vector field. Okay. So let's look what is the formation of these two surface integral. So first of all, we have surface integral of the scalar field. So scalar field here means that our function in terms of, so we have some kind of surface f of x, y, and z. So if we want to evaluate this surface integral for the given sigma here, ds, so we can evaluate by using the following formula. So where r here is the orientation, or is the projection on the xy plane. So we will write the function f y z in terms of x y only. Okay, so we will write z in terms of x y, and then we will substitute in f here. So and then we will write ds in the form where we have the square root of partial derivative of z with respect to x square partial derivative of z with respect to y square plus 1 dA. And here r again, I repeat, it is a projection of the surface on the xy plane. So this is a formulation of the surface integral xy. But sometimes it is much more to project the surface on the xz plane. So the is similar to the first one, where we will replace y here z. So instead of f in terms of x, y, and z, we are going to have f just only in terms of z only. So as usual, this part we can see that the partial derivative of y will be computed with respect to x, and partial derivative of y with respect to z here. And then we take the square of these two partial derivative and together plus with 1 here. These all things here will represent the ds over here. And keep in your mind, this dA is depend on the given question. Sometimes it is much more easier to evaluate in the Cartesian coordinate system, and sometimes it is much more easier to compute in the polar coordinate system. So if you want to evaluate, if you want to project the YZ plane, then that formula here. So let us look one example. So to evaluate the surface integral, so this is a given function f of x, y, z here. And this is a given surface. So we are given the surface cone square root of x squared plus y squared. So this surface are only interested on the between z equal to 1 and z equal to 2. Okay, so to evaluate this surface integral, I um, I already make a step like this, so you can follow to each of the step to evaluate the surface integral. So step 1, sketch the given surface. So this is the given surface, and we are going to sketch what is the surface that we are going to evaluate. And next one, we are going to choose the right formula. So the formula is chosen based on the given surface. So sometimes it is much more easier to project the surface on the XY plane, and sometimes it is much more to project the surface on the on the YZ plane. So to choose the formula here, so it depend on the given the first step here. So it's depend on the given sigma. Okay, and then last one, we are going to before we can evaluate the surface integral, we need to find what is ds. So ds here is given by this formulation. So this formulation also is depend on the what kind of projection that we choose, either on xy plane, xz plane, or yz plane. For example, if you choose on xy plane, then you need to use this formula. Okay, so now let us do the step one by one. So first one, we are going to sketch the given sigma. So this is a cone, the standard cone, z equal to square root of x squared plus y squared. So we can sketch this cone as a given here. And then we know that we are interested on the line z equal to 1 and z equal to 2. So only interested 20 here. So only this part we are interested, or the plane that we want to integrate, or the surface that are interested. Okay, and then so of course we need some extra information uh, in order to evaluate the surface integral. So for example here, when z is equal to 2, so I know that this is when z is equal to 2, this is z equal to 2. And then what I'm going to do, I want to find what is the corresponding value over here. So how to do that one? So just substitute into the formula. So z equal to 2, I'm going to substitute into this one because this is the surface that we are sketching. Okay, and then substitute z equal to 2 over here, and we solve it, then we get 4 equal to x squared plus y squared. So it is a circle over here. That is 4 is equal to x squared plus y squared. So this is how I know this is 2 and here is negative 2. So you can repeat the similar procedure to get the circle, net circle, which is circle with radius 1. 1 equal to x squared plus y squared. So we're done with the first step, sketching everything. So next step, we are going to choose the formula. Based on the given picture here, it is much more easier for me to project the what we call the shape or the surface on the xy plane. So it will be easier for me to evaluate the integration. So that's why I'm choosing the formulation mapping, or the formulation that project on xy plane. Okay, so this is, we are the one who choose this formula. So step number 3, I'm going to find ds. So ds is corresponding to this part. So this is our ds. So for a given ds, so I'm going to find the partial derivative of z with respect to x here. So you can pause the video and evaluate the partial derivative of this one with respect to x. So you will got this equality. And if you evaluate the partial derivative of z with respect to y, you will got this equation. Okay, so you always can pause the video and try to evaluate by yourself. Okay, so if you're done, then you will reach to this formulation. Okay, now we already have everything. So, uh, from here, we can see that we can do some simplification. So this is continuation. So I expand the square over here. So we have x square. So this square root will be vanished. And then it will become x square plus y square. So this part also the same. We have y square. So the square root will be vanished. And we will left with x square plus y square. So since the denominator are the same, so we have x squared plus y squared. Here also we have x squared plus y squared. So therefore we can add these two together and to get x squared plus y squared over x squared plus y squared. So basically this one you can simplify to get 1. And 1 plus 1 is equal to 2 together with square root. We have square root of 2 dA. So now we are ready to evaluate the surface integral. So to evaluate the surface integral, we are going to substitute back to this formula. So what we are going to do first is we are going to replace our z in terms of x and y only. So we know that z is equal to, for given here, z is equal to square root of x squared plus y squared. So I'm going to replace z equal to square root of x squared plus y squared. So one I replace this, so y here just copy, but z I replace with square root of x squared plus y squared. And ds I'm going to replace the value that we have here. So this is our ds. Okay. So now, this is a constant. I will take this constant outside. I will have this equation. And then the square root of r y square x square plus y square. This one just simplify. The square root with the square. And we have y square multiplied by x square plus y square. So back to the sketching here. I know that the form or the region here. So this is my region. So the region is in the circle shape. So therefore, it is much more preferable for me. It is much more preferable for me to evaluate in terms of on using the polar coordinate system. So to use the polar coordinate system, I'm going to change ZA into the RDRD theta. So take out the square root outside here. So changing y square is equal to r square sine square theta, and changing this x square plus y square to become r square. So change everything over here and simplify a little bit this one. So we have r square, we have r square, we have r, then we have r to the power of 5, and we just copy again sine square theta over here. So up until here, we just do the simplification. Now we are going to evaluate the integration. So integration of r to the power of 5 will become r to the power of 6 over 6, and evaluate this value from 1 to 2. We have this 2, and do some simplification. This constant with a constant outside here, you will get this number. So now we are ready to evaluate the sine integral, the sine square over here. So to evaluate this one, I'm going to change. I'm going to use the what we call um, the formulation. So the trigonometric properties. So sine square theta is equal to 1 minus cos 2 theta over 2. So from here, we can take out 2 outside, then evaluate this integral one by one. So I'm going to evaluate 1 and cos 2 theta. So from here, evaluate 1, you will get theta. Evaluate cos 2 theta, we will get sine 2 theta over 2. And then compute from 0 to 2 pi and 0 to 2 pi. So of course, everything here become 0 because sine 0 is 0. Sine 2 pi, sine 4 pi is again, it will become equal to 0. So we just left with the theta here. So we will have equal to 2 pi and 2 we cancel with 4, then we will get this answer. So this is the evaluation or example of the surface integral for vector field. So now let us let us look on the surface integral of vector field. So here we have one another formula here that will be your exercise. So now I want to look on the surface integral of the vector field. So given a surface theta, suppose that surface can be written so this is a formulation how to compute the surface integral of the vector field. So for a given surface sigma here, and then we suppose that that surface can be written in the following form. So we have phi xyz equal to 0. So if n here has a positive orientation, then this is a formulation. So this is how we evaluate the surface integral. So we need to compute the dot product between the nambla phi here, the a with respect to r here. Okay, so of course r is a projection on the xy plane or xz plane or yz plane. So it depends on the given surface. Okay, and then if n has a negative orientation, so this is a formulation. So it's just differ at the negative side here. So you can think that the positive orientation represent the positive axis. So if we have the axis x, y, and z, so all the positive axis here represent the positive orientation. Okay, so now let us look on the one example of the surface integral of vector field. So this example, given sigma be part of the surface of the cone z equal to square root of x squared plus y squared from z equal to 0 and z equal to 1, and a given f as the following. Okay, so now we want to evaluate the surface integral of f for a given n here. So usually in the question, this if n here is not stated, means that n is in positive orientation. So you can safely think that n here is positive orientation if it is not a given. So to evaluate the surface integral of the vector field, first of all, we can write the function phi. So to write the function phi, we are going to move the right hand side here to the left hand side to get this equation. So we will get 0 is equal to z minus square root of x squared plus y squared. So we are going to take everything over here to become our function phi. Okay, so next step is to evaluate the Nambla phi. So to evaluate the Nambla phi, you will know that it is partial derivative with respect to each of the variable. So partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And then we need to put the what we call here the vector I, j, and k. So evaluate the partial derivative of this function with respect to each of the component. You will get this value. So this vector is represent the Nambla phi. And then third step is to evaluate the dot product of f with the Nambla phi. So this is a given f, and this is our Nambla phi. So we are going to evaluate this dot product. Okay, evaluate the dot product between this one. Here is a answer. Sometimes it is much more preferable to simplify the expression, but sometimes you can leave the answer like this. Okay, so the fourth step is to sketch our sigma phi. So sigma is given here is a cone with the center at the origin, and we want the surface from z equal to 0 up until z equal to 1. So we just will sketch the cone started from 0 and up until 1. Okay, so after sketching this one, we'll understand that it is much more preferable to project this surface on the xy plane. So what I'm going to do now is I'm going to substitute everything, the dot product over here into this formula. So replace everything over here, and I'm going to choose dA in term or in polar coordinate system because the region here is a in circle. So changing dA to become r d theta, and then replace the term over here correspondingly. For example, x is equal to r cos theta, y here is equal to r sin theta, and square root of x square plus y square. So you can replace, will become x square plus y square equal to r square together with the square root. You will get r. Okay, so simplify everything over here. So this r you can cancel, and then we will left with this integration. So the limits here, of course, is easy because it's cover all the center here. So r limits coming from 1 up until 0 up until 1. And because it's a whole circle, that of course is going to cover from 0 to 2 pi. So evaluate first with respect to r, we will get r square over 2. Evaluate from 1 to 0 to 1, we will have 1 over 2. So this evaluation of the integral over here is easy. So everything is calculated over here. So you can pause the video and try by yourself. And then the final answer should be equal to pi. Okay, so there is another example here that you can try by your own. So I will stop the video over here. The next video, we will continue with Stokes theorem and also Cauchy theorem. Thank you.